All right, let's have a look at tutorial 7, question 1. And this is dealing with fluidization. So the first thing they say to me is that particles have an average size of 75 microns. So I'll write it on the side here, and we can enter all of this into Excel later on. Okay, so 75 times 10 to the minus 6 is micron. Okay, Sg is equal to 3. So this is the particles. So we're talking about the density of the solid. Okay, because the particles are the solid, and that is 3,000 kilograms per cubic meter. And now they start talking about the gas. So these particles must be fluidized in the gas. So the viscosity of the gas is 0.02 Cp. And by now you should remember that 1 Cp is 1 times 10 to the minus 3 Pascal seconds. That is the SI conversion. Okay. They also tell you that the density of the gas is 1 kilogram per cubic meter. So I'll write it as rho g equals 1 kilogram per cubic meter. Okay. The operating velocity must be the average. Let me just put these here so I remember them. Okay. Now they say to me the operating velocity should be the average of the minimum fluidization velocity and the transfer velocity. So if you had to write that as an Excel function, you'd say UOP, operating velocity, is equal to the average of the UMF and the UT. Transfer velocity, minimum fluidization velocity. Okay. It can be assumed that 90% of the particles are bigger than 45 micron. And so we call this the D90 value. The D90 is equal to 45 E minus 6 times 10 to the minus 6 meters. So what that means is 90% of the particles are bigger than that size, and the place where you use it, I'll just make a mark here for now, so you can also make a mark in your notes. This is used when calculating UT, the transfer velocity. So the transfer velocity is what velocity must you reach in order for particles to be transferred out of your reactor. And we've established that it's okay. This is just like a rule of thumb, a heuristic. It's okay to lose 10% of your particles due to the transfer velocity. So you're allowed to lose 10% of the particles in your reactor when you're using it. Yeah, that's that. Okay. So the packed bed before fluidization. So anything before fluidization, we just put a 0 subscript on. Okay. And then after fluidization gets OP subscript to say at the operating conditions. So the packed bed, the epsilon, initially is equal to 0.4. Remember that's dimensionless. Okay. And the height is 1 meter. So when they talk about the height of the packed bed, they're basically talking about the length of the packed bed, and that is 1 meter. And so remember the opposite of this would be the epsilon at the operating conditions and the length of the bed at the operating conditions. So remember, at the operating conditions, your particles are going to fluidize. So you're going to have a much higher volume of open space to volume of particles. And so you expect your operating epsilon to be higher, and your length of your bed also expands. So you expect the length and the operating epsilon to be bigger. But we know that these two are related by the equation. Length 0 into 1 minus epsilon 0 is equal to length at the operating condition into 1 minus epsilon at the operating condition. And this equation was derived from a basic mass balance. I won't prove it here, but if you are really interested, you can prove it to yourself. It's a volume equation, I believe. So you can just have a look at that. Yeah, it's just a volume equation balance, something like that. Okay, so the first thing they want to know is what will the pressure drop be across the fluidized bed at the operating conditions? So we can always go into Excel and start entering these values, but sometimes it feels like a wild goose chase because you're just entering values randomly and things like that. So I always like to have a strategy planned on the piece of paper. So let's go ahead and develop our strategy. And once we have a strategy on paper, we can go into Excel and start to implement it. So they want me to find the delta P across the bed at operating conditions. So let's talk about how I'm going to do that. Well, delta P over L is equal to, and if I'm looking down, it's because I don't have the equations exactly in my head, but you know, it's better to have the equation accurate than to make a mistake. So I know that delta P over L is equal to this equation here. And so you can see This implies, okay, so I know the gravity, I know the density of the solid, I know the density of the gas, but I do not know the operating epsilon, and I do not know the length. And because this is the operating epsilon, this is the operating length. So you can make a note of that as well. So this implies that delta P is equal to a function of the operating length. Now it's also a function of the operating epsilon, but I won't write it here, and you will see why in just a second. So that's my first note I made to myself. Well, if I want to find delta P, I need to find the operating length. Now, how do I find the operating length? Well, I know that operating length multiplied by 1 minus operating epsilon is equal to L0 into 1 minus epsilon 0. And so once again, I'm given the epsilon 0, the L0, but I do not have the operating epsilon, and I'm trying to find the operating length. So this implies that my operating length is equal to a function of the operating epsilon. And so you can see why I left it out of the first equation. Okay, so it gets more complex than this. How do I find the operating epsilon? Well, the operating epsilon needs to be found implicitly. So that means that my Archimedes number at the operating conditions is equal to 150 into 1 minus epsilon at the operating condition over the operating epsilon multiplied by Reynolds number at the operating conditions plus 1.75 into 1 over epsilon at the operating conditions multiplied by Reynolds number at the operating conditions all squared. And so here, remember that the objective is to find the operating epsilon. But in order for me to do that, I need to know what is my operating Reynolds number and my operating Archimedes number. Everything else I pretty much know. Okay. And so this implies then that the epsilon at the operating conditions is equal to a function of the Archimedes number at the operating conditions and the Reynolds number at the operating conditions. Okay. And to further complicate matters, the Archimedes number at the operating conditions, this one is not so bad. That's equal to the density of the gas times density of the gas minus density of this solid minus density of the gas multiplied by gravity multiplied by the average squared cubed divided by viscosity squared. So we actually have all the information available to calculate the Archimedes number. We have all this information. But then to find the Reynolds number at the operating conditions, that's going to be the d average multiplied by the velocity at the operating conditions multiplied by the density. Remember, as long as it's not specified, it's density of the gas. Okay? And then divided by the mu. So you can see that all of this comes down to, well, Archimedes number we can already know, but the Reynolds number, so this implies that Reynolds number at the operating condition is equal to a function of the operating velocity. And now we've reached the true dependent variable, which is the operating velocity. So let's start by trying to find out. So you can see we've got 4 dependent relationships here, but the main dependent variable is operating velocity. So let's go and start the process of trying to find our operating velocity. So our operating velocity can be, we have 2 equations to determine it. We've got the Bayes equation, or however you say that, and we've got the Wen and Yu equation. Okay, so each of these is going to give me a number, and we'll go into Excel to try and solve it now. Or maybe it's better if I write the equations down here. Okay, so let's just do that quickly. And I'm only writing down the equation just so when you need to write down your notes or something, if you haven't had time to do it yet, then you can just take it from this video. Okay, so the minimum fluidization velocity, according to the Bayes equation, is the solid density minus the gas density to the power of 0.934 multiplied by gravity to the power of 0.934 multiplied by the dp. So remember, this is always d average, and the only time we're going to use that d90 is in the transfer velocity calculation. Sorry, I forgot to mention that the u operating is actually equal to a function of the ut and the u minimum fluidization velocity. And so what we're actually finding here is the u minimum fluidization. Then we're going to find the transfer velocity, and those two are going to help us find the operating velocity. Once you know the operating velocity, you can find the Reynolds number at the operating conditions, which means you can find the epsilon at the operating conditions, which means you can find the length at the operating conditions, which means you can find the delta P. So that's basically just a summary of all these equations up here. All right, all of these equations. But let's just focus on it one step at a time. So this question is not complex, it's just very long. So let's continue. dp to the power of 1.8, and this entire thing is divided by 1110 times mu to the power of 0.87 times density to the power of 0.066. Okay, and this only applies if your dp is less than 100 microns, which it is, and you can go back and double check that. All right, then on your Win and U relation, you need to work out the Archimedes number. So the Archimedes number will equal to rho solid minus rho g. And if you already know this, just skip ahead to where I actually start calculating it. Okay, divided by the mu squared. So once I've calculated this, I know that Archimedes is equal to 1652 times by the Reynolds number at the minimum fluidization velocity plus 24.51 multiplied by the Reynolds number at the minimum fluidization velocity. So I've got Archimedes, I don't know Reynolds, so I can solve that using Goldseek. Once I know what the Reynolds number is at the minimum fluidization velocity, I know that's equal to the d average multiplied by the u at the minimum fluidization velocity multiplied by the density of the gas divided by viscosity. And so therefore, the minimum fluidization velocity would equal to the Reynolds number at the minimum fluidization velocity times viscosity divided by d average times density. Okay, I hope this is making sense. I just rearranged this equation into this one. Okay, so that's that for the minimum fluidization velocity. All right, we'll talk about the transfer velocity just now, but maybe we can go into Excel and work this out some more. I'm just going to split this screen, zoom out a bit. I hope everything is still going to be legible to you. It's kind of legible for me. So let's see how that goes. Okay, so let's enter some values quickly into Excel. We know that the d average is 75 times 10 to the minus 6 meters. Okay, I know that my rho of my solid is 3000 kilograms per cubic meter. I know that my mu is equal to 0.02 multiplied by 1e minus 3 Pascal seconds. I also know that my rho of my, let's just skip a line here, rho of my gas should equal to 1 kg per cubic meter. Okay. Then I can go into this side, and I think I've got a little bit more information. I know what my D90 is. That's 45 times 10 to the minus 6 meters. I know that my epsilon 0 is 0.4, and I know that my L0 is 1 meter. Okay. The epsilon at the operating conditions I don't know, and the length at the operating conditions I also don't know. So now let's skip all the way down to my Bayes and my Win and U equation. So let's give that a shot. So here is my Bayes equation. I know that my U at my minimum fluidization velocity will equal to density of the solid minus density of gas to the power of 0.934 multiplied by 9.81 to the power of 0.934, close brackets, multiplied by, let's get the other half of this equation, d average to the power of 1.8, 8 divided by, now 1110 times mu to the power of 0.87 multiplied by density of the gas to the power of 0.066, close brackets again. So I hope everything checks out there, and that is in meters per second. Okay, now let's talk about Win and U. So remember, the Win and U was a bit more complex than this. So we're going to calculate the Archimedes number first. So the Archimedes number is equal to the density of the gas multiplied by density of the solid minus density of the gas multiplied by 9.81 multiplied by diameter average cubed divided by viscosity squared. Okay, so we've got the Archimedes number. Now for the Archimedes number, we'll need a guess for the Reynolds number, the minimum fluidization velocity. I'm just going to guess 1 here. Okay, now let's put it into my equation. So when I'm doing goal-seek, I like to put in the left-hand side and the right-hand side and calculate left and right-hand side, and then I'll show you what I do now. So the left-hand side of this equation is simply equal to the Archimedes number. That's cool. The right-hand side of this equation is equal to 1652 multiplied by the Reynolds number. Okay, then plus 24.51 multiplied by the Reynolds number again, and that is squared. Hey, let me just check here. I think I may have forgot. Oh, I did remember it. Okay, so it's 1652 times Reynolds number plus 24.51 times the Reynolds number squared, and so that will allow me to calculate the right-hand side. Now I know in the ideal world the difference is equal to left minus right-hand side. Okay. Now I know in the ideal world, if my Reynolds number was correct, then the left-hand side and the right-hand side would, if I subtract those two and calculate the difference between them, should be 0. So I'm going to tell goal-seek, take this difference and make it equal to 0. And you are going to accomplish that by changing the Reynolds number until I achieve a 0 value there. And so it's going to vary the Reynolds number until the left-hand side and the right-hand side are equal to the same thing. So I'll press enter. And now it's got a Reynolds number for me, just like that. And so if I've got the Reynolds number, remember, from this equation on this side, I can now calculate the minimum fluidization velocity. So the minimum fluidization velocity would equal to the Reynolds number multiplied by the viscosity divided by the d average multiplied by the density of the gas. And so that gives me a number, and I want to be able to compare it with the other fluidization velocity. So I'm going to go here to number, change this into a number, and just put a few more decimals on there. So now you can see I've got the option between these two. So I'm just going to highlight them, highlight this one, and put the units in. And remember, if you're working this out on paper, go back to your page and transfer these values over. Write your U minimum fluidization velocity here and your minimum fluidization velocity here. So if I look at these two, I know my first instinct was to say, okay, I want the minimum fluidization velocity, so I'll pick the minimum of the two. But here's a better way to think about it, right? Or here's a correct way to think about it. I'm telling you at 0.005, I could have fluidization, and the other number tells me at 0.006, I could have fluidization. If I design at this smaller velocity to have fluidization, there is a chance that the other number is the correct one. And that means that by the time I reach 0.005, I haven't started fluidizing yet. And so my entire design is based on me fluidizing at this value, but I'm not going to fluidize at this value because I actually fluidize up here. And so your entire design is based on this lower value. You don't achieve fluidization in the reactor, and all your calculations are wrong. So you'd rather take the bigger number, and so that even if the smaller one is correct, you've already achieved fluidization in the reactor. Because remember, your entire process depends on whether you achieve fluidization. And if you do not achieve it at the smaller value, you're going to make a very expensive mistake in your design because you are not going to achieve fluidization. So you always take the bigger of the two to make sure that fluidization is achieved. I hope that makes sense. And so our minimum fluidization velocity will be equal to the one achieved by the Bayes equation. Okay, and I'll put this in green so we know that we're dealing with the correct one. Okay, everybody's happy. Now let's talk about that transfer velocity calculation. So we're going to go back here, let's zoom back in, and let's talk about transfer velocity. Oops, just give me a few seconds. I accidentally closed my notes. Okay, so we are back. Now let's talk about the UT, or the transfer velocity. So the transfer velocity can be calculated using the Schiller equation. And here's how we do that. So what we do is we calculate the Archimedes number, rho solid minus rho gas times G times D90, remember, transfer velocity, this is cubed, divided by the viscosity squared. Once you've determined your Archimedes number, you can now say that Archimedes is equal to 18 times Reynolds number plus 2.7 Reynolds number to the power of 1.68. So again, you know the Archimedes number, but you do not know the Reynolds number. From here, you can calculate the Reynolds number. And if you know the Reynolds number, then your transfer velocity is equal to the Reynolds number multiplied by the viscosity, yes, divided by the density multiplied by the diameter. And that diameter is the D90. Okay. And so we can calculate our transfer velocity. So it's a little bit less complex than the other approaches. So let's go and do that part quickly before this video comes out to be too long. But once again, if you're getting bored, just skip ahead. Okay. So my Archimedes number, let me label this quickly. This is the Schiller equation. Put it in all caps. Let's begin. So the Archimedes number is equal to the density of the gas multiplied by the density of the solid minus the density of the solid minus the density of the gas, okay, multiplied by 9.81 multiplied by the D90 cubed and divide by the viscosity squared. Okay, so that's my Archimedes number. Now I know I have my equation over here. Archimedes equals 18 Reynolds number, so on and so on. So I'm going to guess a Reynolds number of 1 once again, and then I'm going to say left hand side and right hand side. So my left hand side of the equation is simply equal to the Archimedes number. My right hand side is equal to 18 times the guess Reynolds number. It should be F3 plus 2.7 multiplied by the Reynolds number to the power of 1.68. Okay, so that's my right hand side. Now I can calculate the difference, and remember that the difference should be 0 provided that my Reynolds number is correct. So I'm going to go to GoldSeek and say, hey GoldSeek, I want you to make the difference 0, and I want you to achieve that 0 value by changing the value of the Reynolds number. So here's a Reynolds number that I guessed. Please provide me with the correct one. And so it's going to do that, and it gives me this number. And so now I can calculate the transfer velocity, which is just equal to the Reynolds number multiplied by the viscosity divided by the D90 multiplied by the gas density. And that gives me a number which I think is correct. Change this into a number. And something went funny here. So let's see. The Archimedes number is equal to the density multiplied by the solid density times the gas density times gravity multiplied by the D90 cubed. Okay, that is correct. Then the Archimedes number is equal to 18 times the Reynolds number plus 2.7 power of 1.68 Well, that's annoying because now I can't see where the mistake is. Let me check something quickly. My Reynolds number should be 0.347. That's correct. That's correct. Oh, then I messed up this equation. Okay. Problem found. The transfer velocity is determined by the D90, and I use the D average. So this should be using D90. There we go. Okay, now it's correct. Thank you for your patience. Okay, so now I've got the transfer velocity here, 0.15423 meters per second. And remember that all of this work was just to find the operating velocity. So that is equal to the average of the transfer velocity and the minimum fluidization velocity. Okay, so I will also highlight this in green to show that this is where we have our answer. So all of that was just to find the operating velocity. Now that we have the operating velocity, let's continue with the real stuff, which is fluidization. So we know when we are dealing with fluidization, just going to zoom in here, and let's continue. So I know when we're dealing with fluidization velocity, I know the Archimedes number at the operating condition is equal to rho solid minus rho gas multiplied by gravity multiplied by diameter cubed. This is average divided by mu squared. Okay, so I've got all this information, and remember that we could calculate the Archimedes number at the operating conditions from the beginning of the question. We did not need any additional information, but we did need the operating velocity to find the Reynolds number. So that's D average times U operating, which we finally have after all that hard work, times density of the gas divided by viscosity of the gas. So we can also calculate the Reynolds number. So we've got the Archimedes, we've got the Reynolds done. If we've got that done, you can go back to our equations right at the beginning. I said, okay, if I know the Archimedes and the Reynolds number, then I can work out the epsilon at the operating conditions. So we've already written down that equation, the implicit one. Let me just check that I have written it down for you. Yes, it's this one here. And so once I have that, I can substitute it into the other equation. So I'm not going to write those equations again. Let's just continue and start substituting. Okay, if you need the equations, you can always just rewind. So let me move this over to the side, and let's start working at the operating conditions. Okay, so the Archimedes number at the operating condition is equal to density of the gas multiplied by density of the solid minus density of the gas multiplied by 9.81 multiplied by diameter, average diameter cubed, and then divide by viscosity squared. Yeah, there we go. Okay, now the Reynolds number at the operating conditions is equal to D average times operating velocity times density of the gas divided by mu of the gas. Okay, so everyone is happy with that, with my Archimedes number and my Reynolds number at the operating conditions. So now I can start to do things implicitly. So I can say, okay, left-hand side and right-hand side. And remember, the objective here is to find the epsilon at the operating conditions. So my left-hand side is just equal to the Archimedes number at the operating conditions. My right-hand side is equal to 150 multiplied by, now bear with me, 1 minus the guess epsilon divided by epsilon, close bracket, multiplied by Reynolds number at the operating conditions, plus 1.75 multiplied by 1 over epsilon at the operating conditions multiplied by Reynolds number at the operating conditions squared. Okay, and my guess for epsilon would be 0.4. But remember, we started off with 0.4 as the initial value, so we're expecting it to be something like 0.5, 0.6, 0.7. Okay, so I'm going to calculate the difference here between the left-hand side and the right-hand side. And I'm going to tell Goldseek, in the ideal world, this difference would be 0, and that would be when I have the correct epsilon value. So please, can you vary the epsilon value such that my left-hand side equals my right-hand side? And you can see I get 0.594. So my epsilon at the operating conditions is 0.595. Okay. So if I've got epsilon at the operating conditions, do you agree that I can now find the length or the height of the bed at the operating conditions? So remember that equation from earlier? That was equal to L0 multiplied by 1 minus epsilon 0 divided by epsilon, divided by 1 minus epsilon at the operating conditions. And so my bed length is actually 1.5 meters. That's once it fluidizes. And now if I know the operating length, I can work out the delta P. So the delta P was equal to, let me find that equation quickly. Oh, there's it. Okay, so the delta P is equal to the operating length multiplied by 1 minus the epsilon at the operating condition multiplied by the density of the solid minus the density of the gas multiplied by 9.81. Let me put a multiplication sign here. Okay, and remember this answer is in pascals because we're dealing with everything in SI, so your SI unit for pressure is pascal. Then if you want to convert that, you just take this number and you divide by 1,000, and that gives you kPa. So my pressure drop across the bed is 17.65 kPa, and that took us 31 minutes. But I hope it makes sense. Okay. Then part B of the question asks you, okay, is it particulate or aggressive fluidization? So quickly, we can just make a note of this. Okay. There are 3 ways to determine it for part B. So the first thing I want you to know is that there is an equation called the Wilhelm and Quark equation. And so that just tells you that the FR value is equal to U at the minimum fluidization multiplied by the D average multiplied by G. So if you can calculate this, okay, and it's less than 1, then you've got particulate, greater than 1, you've got aggressive flow. Okay, then the second equation you have is the R&J, Romero and Johansson, or as I like to call it, the Ray-J equation. So if you've got the Ray-J equation, it's FR at the minimum fluidization velocity times by Reynolds at the minimum fluidization multiplied by solid density minus gas density over gas density times length at the minimum fluidization divided by dB. And what you do is you make this equal to 100. So basically what you do in this case is, you know what the FR is, you know what the Reynolds is, you know what this is, but you don't know what the L over D ratio is. But you do know that for any reasonably sized reactor, the L over D ratio is between 3 and 5. And so you just determine for which values do I get between 3 and 5, or for which values will give me 100. And if those values are way outside the range of between 3 and 5, then you make your conclusion from there. And then, of course, the third option is to use the Geldart chart, or however you pronounce that. So let's go and work out question B using the first option that I gave you here, which is the FR value. Okay, and the idea is that if you can calculate for 2 out of 3 cases, 2 out of 3 wins. Okay, so FR is equal to the minimum UMF, minimum fluidization velocity squared, divided by 9.81 times the average diameter of the particles. Okay, so that's, you can convert this into a number, 0.05, and so you can say that's less than 1, and so you know that according to the Wilhelm and Quark equation, we have particulate fluidization. Now let's talk about the Ray-J equation. Okay, that is equal to, let's work out left-hand side and right-hand side, okay? So on my left-hand side, I'm going to need the Reynolds number at the minimum fluidization velocity. So I'm sure I've calculated it somewhere, but I'm just going to calculate it again. Density of the gas divided by viscosity. No. Density of the gas divided by viscosity. Okay, and the other thing I'm going to need here is the L over D ratio. And I'm going to guess that to be about 5. Okay. And so, yes, so my left-hand side is going to equal to I'm dealing with this equation, okay? The R and J equation. So that's equal to the FR value, which is here, multiplied by the Reynolds number at the minimum fluidization, multiplied by rho solid minus rho gas, divided by rho gas. There we go. Multiplied by L over D, close brackets. And so the right-hand side I will make equal to 100. Okay. And so this difference I would like to calculate. So the left-hand side minus the right-hand side. So we're going to go into data, go to what if analysis, and go to goal seek. And say, hey, goal seek, you see this difference? I want you to change it by I want you to change this difference to 0 by changing the L over D ratio and say OK. And so the L over D ratio would need to be 28 for us to exceed the 100. And so because this is a straightforward equation, you can see that if L over D is bigger, the value on the right hand side gets bigger. So my L over D needs to be bigger than 28 for me to exceed 100. And because most reasonably designed reactors are between 3 and 5, then my value on the left hand side is going to be way smaller than 100. So I hope this makes sense. So if the left hand side uses between 3 and 5, the left hand side is much smaller, so we will never reach 100. And so most of the time, if we have a reasonably designed reactor, we're in particulate flow. And so your last one, I'll put down here is the Tut chart. I will open on the left hand side. Okay, so what this chart tells you is first work out the particle size in millimeters. So I'm usually quite bad at this. So what I'll do is I'll just go back to the Excel sheet, take my millimeter number and times it by 1,000. So I'm actually at 0.075 millimeters. Let me just check that quickly. Yeah, so I'm at 0.075 millimeters. Okay, so that means in this picture, remember it's a log scale, so I'm probably sitting quite close to the end here, 0.075. Okay, and then my particle density minus my gas density. So the particle density was 3,000 and the gas density was 1. 3,000 minus 1, 2,999. So if I'm sitting at 2,999, I'm probably sitting pretty close to the end of region A, but I'm probably still in region A. And what do we know about region A? Without bubbles. And so even here, according to the Tut chart, we are in region A. So no bubbles. And so all three of our correlations agree that we will have particulate fluidization. Okay, so I hope you found this helpful. Thank you very much for watching. Thank you for your patience. And yeah, I will see you in the next video. Goodbye.